This is Lab 1 of Constant Velocity over Time. The purpose of this lab was to model the differences between an experimental object moving at constant velocity versus the predicted computational model. There were experimental discrepancies due to other forces involved, which I'll talk about later. The system is the object that we are studying, which is the toy car in this case. The surroundings is everything else. This lab was based on Newton's first law and second law, and Newton's first law mainly stated that an object in motion remains in motion unless acted upon a net force. In this lab, we assumed the net force was zero. Newton's second law related net interaction between the system and surroundings to the observed motion. So the net force was equal to the change in momentum over change in time, and since there was no change in velocity over here, there was no change in momentum and therefore a zero net force. This was seen in the velocity update formula. Since there was no net force, the velocity final equals velocity initial, and then the position was updated with the position update formula with the same average velocity. This is a representation of the forces involved. Since the normal force and the gravitational force canceled out, there was a zero net force and constant velocity. The initial velocity was 0.5 meters per second in the x direction, and the initial position was 0 in all directions meters. The main result of the lab with the preview is both were similar in constant velocity over time, except the experimental increased position at a faster rate towards the end due to discrepancies, which I'll talk about in the discussion. This was the experimental lab where I measured the change in position over change in time of the toy car, and the frame rate was 0.033 seconds, the mass of the car was 0.04 kilograms, and the diameter of the car was 0.1 meters. These were the initial conditions, and the final time was 0.4 seconds. This is how I calculated the initial velocity. The initial position was 0, and the position 1 was seen here, and then I measured the displacement over change in time to calculate the initial velocity. These were the initial conditions in the predicted model with the initial position and velocity, and the time of the delta t, which were the frames per second. This was the velocity update and position update formulas in the computational model that I put in. This was the computational model iteration that I used to update the velocity and position, and then I also advanced the clock with t equals t plus delta t, and this was all less than 0.4 seconds because that's how long the video took. These were the results of the predicted model. So as you can see, the position versus time graph, it had a constant linear slope, which resulted in a constant velocity over time. So, the position was not constant, it was increasing at the same rate. The experimental versus computational model of graph showed that the experimental increased at a faster rate towards the end, which you will see that they had the same initial position and velocity, and the net force was set equal to 0 in the computational, but possible external factors could have influenced the net force in the experimental, which resulted in that increase in velocity towards the end. Possible sources of error included other net forces acting on the car, errors in tracking the car with the tracker software, and errors in placement of the center of the mass of the car, and it could have had motion in other directions. So what if the axes were flipped? The right would be the negative x direction, so it would increase in a more negative position. The magnitude of the velocity would still be the same, so it would still have that same number, but it would just be negative because it would be going in the other direction according to the axes. So on the position versus time graph, it would be reflected across the x-axis with the line sloping up and to the left, which would mean it would have a negative slope, resulting in a negative velocity. So is it possible to say how many pushes and pulls are added together to give zero net force? It's not really possible to see all the net forces acting on the object. Like, we know that there's the normal force upwards and the gravitational force pulling downwards, but we don't really know exactly all the other forces that are at hand, such as like air resistance and friction, and there's no way to tell like all of these forces. Thank you.